Thank you very much. So it's my great pleasure to be here today. Thank you for the invitation and the kind introduction. Thanks everyone for staying until the end. I hope I can give you a bit of a view of how we think of robotics and intelligent maintenance, in the sense that we can take inspiration from nature, because nature, natural systems, insects, animals in general, maintain their own nests very well, right? Is there something we can learn from them that we can apply directly to robotics and to intelligent maintenance? So this is a picture of how a future could look like, where robots, humans, the built environment, the natural environment is seamlessly and synergetically integrated. So I think this is a vision where we can get to, where all this works in harmony and gives a bit of a life-supportive vision of the future. Now, if you think about robotics or drones today, there is, of course, the established supply chain based on imaging, photography, 3D mapping, and database services on top of the data. So you collect some visual data and you do something interesting with that. This has value, is applied in industry today, so it's really something that's not going away. The future, however, will be not just focusing on the data or on the visual inspection, but include the ability to interact with the environment, meaning placing sensor, inspecting the surfaces of structures, of infrastructure, taking samples, and so on, repairing the infrastructure. And so this is relevant for the built environment, for aging assets. It is relevant in construction, in mining, but also for offshore infrastructure maintenance, as well as for environmental infrastructure. And offshore, I would like to emphasize, following the previous talk, on the extension of the life cycle. So many of these assets have been built for 25 or so years. They're coming to the end now of the first life cycle, so they need to be extended. So I think there's a big need in having robotic solutions that can help this to happen. Now, if you look at the market size just for the built environment, it's here 1.9 billion, but most importantly, it's going to increase by a factor of about 10, even in relatively conservative estimates. Same for construction. So this is the drone market related to construction, is also going to increase tenfold. So I think it's clear that drones and robotics are not going to go away. They're going to start, and it's only going to be more of that. The reason for that is that it builds into the inspection and monitoring services, into condition assessment, predictive maintenance, safety, life cycle optimization, and so on. And there are a number of ISO standards that are relevant to that. Of course, the cost savings are one, labor related, so safety, fewer humans in risky environments, but it's also linked to preventive maintenance and efficient compliance. So documentation of these standards, collecting the data, and so on. Now, a criticism of showing something like this is that ISO doesn't say you have to use robots. And of course, you don't have to. But still, the de facto reality is that if robots are more effective and cheaper, people will use that. Companies will use that, and will slowly get into the ISO standards being built in. So this still, even though it's in the beginning now, will be the future. Now, at the Laboratory of Sustainability Robotics, we focus on building robots that can serve you in that way. So we built the Swiss Army knife of environmental sensing that can collect the data, but also influence the environment to do maintenance, repair, and climate action tasks. This is relevant for smart cities, infrastructure, but also for climate monitoring, water health, forest health, and so on. Now, how do we do that, right? So, and if you look at nature, coming back to the beginning, we can see a few things that I find very interesting. One is that the bee here, for example, uses sensing, control, and navigation on board, right? With the brain, the eyes, the antennas, also complex aerodynamics, but also the materials and structures and actuators are co-evolved. And that's the important part. It's not like a bee started in simulation and then built a dead body and then put some life into it and then it starts to fly, right? To optimize its autonomy, like robots are built today. But it co-evolves the structure, the body, the actuators, the nervous system, the learning, the behavior, the aerodynamics, all in tandem. So it happens in parallel in a circular way. And this, I think, is important in terms of the philosophy of how we can build such robots. So let me give an example. Let's say we want to have a robot that flies and attaches to a surface. So we can do that by having a lot of control planning and sensing on board, have a flight controller that we pitch up and attach. Eagles do that, larger robots do that. But when we are very small in size, when the size of the robot is a few millimeters, when the weight of the robot is 200 milligrams, like the RoboBee, we cannot do that. The computers are not powerful enough. The sensors are too heavy. So what can we do then? In that case, we have to rely on the embodied intelligence or the mechanical intelligence of the body that can help in some of those tasks. So this means that the bumblebee, for example, or the fly, they use their antennas and their legs to balance themselves on the surface, dampen the impact, and like this transition to the surface out of flight. So in fact, if we want to create lifelike robots, we have to do both the digital intelligence and the physical intelligence. So having different levels of intelligence that are co-evolved in order to achieve that. And this is the biological lifelike approach. Okay, so a few case studies of what this means now for applications or for the impact. One of them is on forest health. And in the forest, one problem is the crown loss of ash trees. So the ash dieback disease. Are you familiar with that? Somebody, I don't know, somebody likes forest, yes, I'm nodding. So ash trees really suffer, like 95% or so are in the UK are affected from ash dieback disease. It's a catastrophe for the ash trees. And what happens is that they lose their leaves, right? So now we have a system that uses data augmentation, so having labeled data sets combined with synthetic data sets that we created in a game engine, in the Unity game engine. And then we use the YOLO machine learning approach, neural networks, to estimate the density of these trees. By doing that, we then have a method, basically, that we can fly through the forest, collect the data of the trees, and identify the relative or absolute leaf density of the trees. Now, this is very efficient in comparison to manual methods of how this is done today or beforehand. So this type of same approach are used also for crack detection on solar cells and on other examples where also this kind of combination of field data and synthetic data can be very valuable. So the hybrid data sets. Good. Now, if you want to fly through the forest, of course, it's very challenging, but luckily we have nature as a model. And one thing that nature does very well is to use optic flow-based autonomous flight. Optic flow, if you know, is the relationship between the velocity of the vehicle to the distance to the obstacle. So if you have an obstacle that approaches an obstacle, the obstacle increases in size on the retina. It's like you walk towards the wall becomes bigger, right? And you can use this expansion, this divergence field as a proxy to the distance to the obstacle. This is fine, it's used in nature, it's used in robotics, but has the problem that if the environment is three-dimensional, it gives you false alarms, right? You can get spikes of those data sets, and then this gives you some false information. Because of that, we use the fixtures wall hypothesis, where we combine the optic flow divergence input with some other state vectors on the IMU to then have an ex-ante Kalman filter and have an observation that can give a much better estimate on the actual distance, even in three-dimensional environments. This allows us to build robots that can fly, detect obstacles, and stop in front of the obstacles, for example, in a forest environment, as you see here. So it flies, detects the bushes or the trees, stops there, or can even enter through narrow openings in the forest. Now, this is achieved with very minimal sensing. It's the same sensors that you have on the mouse, the optic flow sensor. So very lightweight, very low computation, and using a microchip, so a very low weight and low power consumption microchip to calculate this optic flow like that. So the whole sensor, computer, battery package for this is about 20 grams. Still, it allows the robot to fly autonomously through the obstacles, avoid obstacles, go through narrow openings, and so on. So it's a minimalist strategy that helps for autonomy, not requiring some complex sensors. So I think this approach is quite powerful. We can then combine it with sensors, tactile sensors, to interaction with the environment, like the antennas on animals, to then do sensor placement, surface sampling, and so on. Now, can we use the impact or the contact in a way to actually help in the mobility, right? And this is something that we explored here, where we looked into origami-based structures to reduce the impact velocity or impact impact energy, and also like this make the systems more resilient. This means it's an origami ring that is rotational, so it decouples the yawing moment on impact, and it is soft, so it decreases the peak force on the impact. These two things are very important because this is what makes it crash when it touches the surface. So by having this origami ring, we can optimize parameterize and optimize it. It allows us to survive 5 small crashes and like this move efficiently through the environment, even if there is a crash. So the combination of minimalist sensing, low energy, low computational cost sensing with resilience on the physical element, I think this combination is very powerful and can be applied to various robots, but it's an important paradigm, I think. Now, okay, so the next question then is, what if we use the impact to augment capability, right? Can we use the crash to actually do something useful or help in the transition? And this is something that we explored here, where we have this metamorphic full body perching. So it's a robot that flies, then has a metamorphic body that has a composite structure that is pre-tensed. So it has some flexible sheets that are embedded into the three-dimensional structure, allowing it to fly, then land, and then hug the tree. So it's like a tree-hugging robot, if you want. It really likes nature as well. So, and then by doing that, it can then stabilize itself and be quite effective in outdoor environments. So the intermittent locomotion, as you might call it, that it flies and attaches and then flies off again. During this attached state, it can actually sense much longer with lower energy needs. And like this can be a good method for environmental monitoring or infrastructure monitoring and so on. But here, the physical interaction is used to augment the capability and enabling the perching motion. Now, what happens if we cannot approach the surface? What if the surface is obstructed, like you see here in this tree that has these branches? Then we looked into ways how to place the sensors on distance. And this is basically the idea that you have a flying robot that has a dart-like system, so the sensor you want to place, and then calculates the trajectory of placing these sensors remotely. Then, if it calculates it right, it can place it like this on distance with a quite high precision, because it's quite easy to calculate the trajectory. So it's a few centimeters and a few meters distance. Then you can place different types of sensors. This work was funded by the like forest science community, but also by the nuclear community, where we wanted to place sensors on distance without having to engage with the beryllium surfaces, which are very toxic and so on. And so often this can be a good method to place them remotely. We then tested them in the forest, where often you want to climb up to measure the data. And here it flies and can then at different heights place the sensor on the tree, as you've seen. So what do we sense then? What would you sense in the forest? Of course, I don't know, temperature, light irrigation. But one important thing that we measured also is the acoustic signature. So it's the sounds of the environment. And by measuring the sounds, we get this spectrum, which we can then analyze to create, to get insights onto the species in the environment. So the bird sounds, getting insights onto how many birds there are and how many different species there are. So this is the machine learning algorithms on top of the sensor, the acoustic data. So this allows us then to quantify how many birds are where, how many birds are where. So being a method of automatic sensor placement that is more cheap and faster than manual placement. Just confused that my mouse moves around. I'm not sure why I'm not touching it. A bit worrisome, but let's see. Okay, so the next question then was, is there a way how to place these sensors and not having to recover them? So can we make them biodegradable, right? So that we leave them in the environment and not have to recover that. So this is something we're working on for a while. And we wrote this perspective paper here, what, 2 years ago to 3 years ago. looking at ways how we can benefit from bioelectronics to create those next generation of transient robots, as we call them. So robots that operate in the environment and then stay in the environment and biodegrade without influencing negatively the environments, like the e-waste reduction, if you want. And so there's a few things. So in the near future, this will be humidity, temperature, but in the midterm and long term, it will include complex data, acoustic data, and other types of data that can really help in this kind of sensing. Yeah, the mouse is moving around, huh? Should I try maybe maybe it's this one, huh? Yeah, it's something to do with this. Maybe I'll try. Okay, so this whole field we call transient robotics. And of course, if you think about a robot, it consists of a sensor, the actuator, and the structure. So I'll just give you one example for each to outline a bit how we approach this. On the structure side, we work with something called cellulose composite cryogels, which are basically cellulose materials in gelatin matrices, which can then be molded into place, freeze-dried, and then creating these kind of porous structures. Depending on the mix and the process parameters, we can optimize that to have certain performance metrics in terms of structural resilience, while also having certain biodegradation metrics so that it can die or kind of biodegrade when we want and have certain performance when we want. So it's some control mechanism on the biodegradation. In terms of the sensing, we work with biodegradable inks, such as carbon ink, which we can screen print or inkjet print on these cellulose substrates to then create sensors, as you see here, that is like the skin of the robot that can measure the deflection, measure the extension or different types of parameters, maybe temperature, humidity, and like this be fully biodegradable electronics and sensors on the skin of the robot. The actuation, the first ones we explored is using humidity-triggered actuators. This means that it's a layered approach, and then one layer expands as it gets more wet or it gets humid, and then it creates a motion. This is something used in plants a lot to deploy the seeds. Maybe you've seen that, like every morning they expel the seeds. And this type of mechanisms can be used in robotics too as a actuation methods that is triggered psychically or just once from the environmental humidity. So the robots we build here, I mean, the glider is a glider that has a petal-like structure that opens when it gets humid and then exposes a pH sensor using litmus materials that then changes the color based on the pH level of the environment. So this is a self-deploying pH sensing system that self-measures when it experiences humidity, but uses zero electronics and zero non-biodegradable materials. So it's an example of some steps in this direction. So eventually, the goal here is to think of robotics in a circular economy way. So not that we build the robot, then use it, and then throw it away, but we build it, use it, it then biodegrades or dies in the environment, and then maybe can even regrow. So can we farm the robots, that they would heal, self-heal, or regrow, and like this be used again? So bio-inspired. The next one I would like to emphasize is this idea to go away from biology, but go towards superheroes. And one of my favorite heroes in that way is the Spider-Man. And Spider-Man is able, of course, you shoot these anchors and swing through the cities, right? And we found it quite inspiring. And so we looked into ways how we can build spider-like structures with the robots. So can we use tensile elements to help in the motion, help in the sensing, help in the deployment or operation of these robots? So then we took these very small robots and integrated a silk deployment spool type system, which has a lot of advantages actually, because it can attach anchors to structures that are not predictable. So a tree has a three-dimensional surface. It's very hard to make an anchor, but by using the string, it can weave around and like this make support scaffolds for other robots that can then attach to this, observe the environment, and even maybe do sensing or repair tasks using this kind of tensile manufacturing. And so we were quite inspired by that for a while. For quite a few years, we worked on this. We built a variety of robots, one being the weaving robots here, with the idea to extend the net and then measure the environmental motion or environmental kind of performance, or using strings for perching so that the robot attaches an anchor and then can perch down to sustain itself in air and like this sense the environment. As you see, so this is something that also we patented, and so it's quite useful for industrial inspection and is being also now used. Or tensile element that can be combined with soft self-adaptive grippers that are fully passive, that can like this attach to trees, attach to structures, and enable this physical interaction without the need for complex sensing or kind of actuators on the end effector. So fully passive, fully benefiting from the passive compliance of the material or of the string that adapts naturally to the environment. Now we then combine this with model predictive controllers, admittance control, as well to measure the interaction and also measure the environmental forces on the environment, on the robot from the environment. So we can measure compliance, for example, of the tree. So we also published a book on this, edited the book with some chapters on this type of work. So if you're interested in this type of work, there's a lot of other interesting chapters there too. Good. So one thing I would like to emphasize here is the way how to control this. Of course, we can use PID controllers or neural networks, but the neural networks are interesting because we can have more complex motion like this perching approach, but we can start in simulation, evolve the controllers there, and then here using reinforcement learning-based methods to make this perching motion using a reward function that is about following the trajectory that we give it, as well as move continuously and safely along this trajectory. And by doing that, we can then evolve this type of motion where it can fly and self-tether itself to the environment. And so I think this is also quite interesting to have this relatively complex motion that can be can benefit from neural networks to do the flight control and not just the environmental data collection and insights based on the data, but also on the robot itself to have a contribution. Good. Another example I would like to give you, which I think is very relevant for intelligent maintenance and inspection, and that's this here. So I'm not sure if you remember this, but in 2017 it was, 14th of June 2017, there was the Grenfell Tower fire in London, right? You probably remember that, yeah? And so 72 people, at least 72 people died in that, and it was a catastrophe, of course. I was living in London, actually here somewhere not far from this, and I was driving to work in the mornings, and this was burning for 3 days. It was fuming, and it was terrible, really. And so somebody called me that next day, asking whether we have a robot, a flying robot that can go inside of this to look for people, look for structural damage, just to get insights, because you cannot go inside as a human firefighter very easily. Now, we didn't have that, unfortunately, but it did inspire the idea to create robots that could do that. You know, can we build robots that can fly inside of the fire, get data quickly, helping firefighters, helping to save people inside? Eventually, this is the robot. It's called the fire drone. The idea is to have a robot that is heat resilient. And how we achieve this is by looking at biology and different heat management systems, how biology does that. From Arctic animals to insects and structure building animals that have heat management built into them. And so we developed a new type of aerogel material. Aerogel, if you know, it's a very heat resilient, lightweight material. So it's a polyamide 3D printable material here using fiber reinforcement. So it doesn't shrink when it gets hot. Normal aerogels are silica based and they shrink and are very brittle. So we had to use a new one, build a new one with our partners at EMPA. And we had a new arrangement of the motors, being the motors inside of the body, not at the periphery of the robot, and having a cooling system that can cool down and manage the heat inside. By doing all of this, we have a system now that can allow us to fly in relatively hot environments, as here, so around the fire, inside of the fire, and much longer in a much more resilient manner than current robots. And by doing that, it can collect the data faster, cheaper, and at lower risk compared to current methods, which are largely manual. So I think this idea to create robots that can operate in extreme environments where really you don't want to have humans involved in or have humans being exposed to those environments is a good example of how robotics can help all of us. Now, when we published this, we did some press coverage or press release, and so we had a lot of interest from industry, and everyone wanted to buy one, use that, you know, because you can do inspection with that like any other drone, but you can also do it when it's hot. So it's quite interesting. Because of that, we launched a startup now. We call it Far Drone. It passed several awards and so on. So if you're interested in that, please reach out. Okay, so the second last theme I would like to briefly mention is the idea that we can use robots not just for measuring and sensor placement, but what if we can use it to do repair? What if we can use it to build houses? What if they can collectively actually manufacture cities on Mars? And of course, it sounds a bit ambitious. So how could it look like? It could look like this. You have the robots, they fly collectively, they maybe even collect environmental material, deposit it from flight to create layers of structures, and like this act like a flying 3D printing head that can deposit material and build up larger structures. This, of course, not by themselves, but in collaboration with humans and with ground robots, climbing robots. And in many ways, this is a paradigm for the future of construction also on Earth, where flying ground robots and humans will work together. Now, we had these two papers where we looked into the review of how biology does that, how the future looks like. And there's an interesting analogy to how biology builds, because biology builds in a different way than how humans build. So humans build, like you have an architect, you have a blueprint, and you try to replicate the blueprint as good as you can. Nature doesn't do that, I mean, as far as I know. So there's no kind of architect B, right, that tries to make the blueprint and everyone then tries to execute. Nature works based on principles that are local, informed by the local interaction between the agents and the local interaction with the environment. So they build something based on what is being built, the next step is being built. So this gives these rules or templated construction principles, even emergent structures that are based on local principles and decentralized information sharing. Now, this we try to implement and build a robot that can do the same philosophy of construction. The robot we build eventually is this here. It's a flying robot. It has a delta arm manipulator, can stabilize the extrusion head, and then 3D print from flight high performance cement material in this case. So you can do this different layers. The challenge, of course, is to make this material strong enough, light enough, hardening fast enough, while being extrudable enough for this to work all together. All this while also optimizing the trajectory, the precision of the process, and the hardware, as well as the multi-agent coordination and the architecture of what is being built with that. So it's a very multidisciplinary effort. Of course, cement, if you think about it, it's you print and it stays in place, right? It stays where you put it, more or less. But many other materials don't do that. For example, polyurethane foam gives you a larger volume of the material, but it gives very little predictability on how it behaves when you print it, right? It's a chemical process, it expands. And because of that, we had to integrate a scanning in the loop. So a 3D printer, like I said, makes one layer and then scans the layer. And based on that, prints the next layer. So it's a closed loop form of scanning, printing, while also not just optimizing the approach to make it scalable, but also giving us the operational and performance metrics of the process to estimate how much material is being printed, how well it performs, and so on. So this, again, approach, even though we applied it here to a tower with 72 layers, like a 2-meter tower. But the same approach can be used in repair of infrastructure in general, where we have a repair, an automated repair process. Then you have a scanning process, and then again, doing the repair, having the closed loop nature to this. So the same framework is applicable. Eventually, we have not just one robot, but we want to have several robots that would do that. So how would this look like? So we'd have multi-agent systems. They coordinate the motion, but they coordinate it based on the behavior of each other agent. So it's not a centralized controller, it's a decentralized one that really looks into what each agent has built and then allocates the task locally to the other agents to then optimize the trajectories to save energy, improve the speed, and reduce the material that is being used to print. So we showed this with several thousands of agents in simulation, building very large structures, but in real experiments with fewer agents, I think 3 here in this example. So the whole thing came out in 2022, which made us very happy, of course, but partially also because it's a very multidisciplinary effort where we really had to pull together material science, robotic, control, hardware, architecture to build this type of system. We then went to the Architectural Biennale in Venice, where we showed that as an exhibit for 6 months, with the idea of how now architecture could benefit from this, right? Architecture doesn't build like that, but if you can build like this, what does it liberate? What kind of design freedoms do you have with this type of process? Okay, eventually it's not just about 3D printing and tensile structure. There are other ways of aerial additive manufacturing, from discrete to continuous to tensile and so on. So there's a variety of those approaches. There are benefits and drawbacks on each. And I think an important element is the autonomy, like how autonomous is it? So most of it, which we have today in terms of assembly with robots, flying robots, is predefined trajectories of the robot. The next step is the physical interaction. So some kind of interaction, like placing blocks, you're kind of moderating the kind of forces on assembly. But interesting, I think, is to have the online flight and task planning. This is the multi-agent kind of coordination, as I mentioned. But then having the scanning in the loop and the structural assessment in the loop. So you build something, you scan it, you estimate of how strong it is, and then you build based on that the next step. So I think that's the holy grail in some way of this type of process. You don't just have predefined motion, but you have adaptive, fully closed loop motion that come together. So I think with this, we can build robots and systems that could be even fully autonomously operating on construction sites. Now, a shoot off from this type of work is this here. So it's a robot that can do repair tasks for industry. So that's the applied arm, if you want, of all of this, right? Doing 3D printing tasks or repair on cracks, on damages from flight with very high precision of a few millimeters with different materials. So we have this robot, we have the framework, we have the controller, we have the user interfaces, and we are now doing industry projects to manifest it and bring value to industry. So if this is of interest, also please don't hesitate to reach out. Good. So the last example is the question of how we can do inspection, not just in air, on ground, or in construction, but also underwater, right? I mean, offshore energy requires a lot of inspection of pipelines, structures, oil and gas platforms, and also environmental aspects such as biodiversity, water health, acidity in the coral reefs, or any kind of structural damage in the Arctic, where often it's very inaccessible. So we looked into ways how we could build robots that would fly and then dive into the water doing this type of inspection. So aerial-aquatic robots. One example of that is here, which is the Medusa robot. It is a robot that can land on the water and then deploy an underwater tentacle, if you want, like Medusa. And like this, do sensing and kind of manipulation tasks in the environment. Here you see an example of that in Lake Zurich, which we did also the test together with EAVAC, which is the Water Sciences Institute in Switzerland. And so it can land, fly, land, and then has this underwater tentacle to do water health monitoring. So here we are very interested in the chlorophyll A measurement, which is a correlation to the cyanobacteria, you know, which is a big problem in the algae growth in the lakes, so the lakes can become toxic. And so we use this to monitor and sample this environment in that way, getting insights and having a method of remote sensing in aquatic environments. We then combined this with static sensors or established sensors of this chlorophyll A. And as you see here, actually gives very similar data. So it is an autonomous method that is validated against common methods of doing that. Now, for us, this, of course, wasn't enough in terms of approach. So we wanted to have a system that can fully fly and then out of flight, dive into the water, do something, and then fly out of water again, right? And by this is, of course, because there are many diving birds or flying fish, right? And we looked at that and thought, can we build that? Can we benefit from that? So we quickly realized that there is a lot of mathematics to understand in this, a lot of physics, multi-flow physics, control questions, morphology change question, optimization on the whole motion and everything like that, that needs to be accounted for. And so we're working on that for about 12 years now. And one example is this floating robot that is in the water. So it's like a water robot, but then jumps over obstacles in the water. So they would then float, then jet out of the water, glide back into the water, and then refill to jump again. Flying fish type of robot. Now, they're not just flying fish, they're also flying squid, right? By the way, they're fully soft winged structures. They're kind of animals that jump out and use that to escape or to migrate. It's not really known. So we looked into a way how to have high power propulsion, and one interesting one was calcium carbide. And if you take calcium carbide and you mix it with water, it creates acetylene gas. Acetylene gas burns quite well and can be used then to create those combustions to then eject the water from the body. Like this, we have like a water rocket type of structure that uses environmental water and a little bit of calcium carbide to create those combustions. So we're quite excited about that and build eventually a robot that looks like this. Now skip about 4 years of work. At the end, looks like this, being basically this kind of structure of about 40 centimeters and having this combustion in the body, having the whole mechanism. You see the spray, so the jet and the spray, and then a bit of fumes, right? And then keeps on jumping. So like this, it can jump a distance of 23 meters using 0.3 grams of calcium carbide. So it's a quite powerful combustion that happens and a quite powerful method of getting out of the water. Once you're in air, you can keep on flying quite readily. So really the transition is the complex one, which needs a lot of power. We also built in collaboration with Harvard University, who built these robo-bee, so the robotic bees that are the size of a real bee. We looked into that and collaborated on building this thruster system using hydrolysis. So you could use hydrolysis, you capture hydrogen, oxygen, and can ignite that, then boost the vehicle out of water, as you see here as well. So same idea, same combustion idea, but at a smaller scale, and having also very highly powerful kind of transition from underwater to air. Another example related is here, which is not using the motion of a thruster, but using the motion of the environment. So can we do something like hitchhiking, right? Can we have a robot that flies into the water, then attaches to an underwater fish or a boat, then uses that for motion? So here it's also collaboration with the group of Li Wen on making these soft adhesive discs that are inspired from the remora fish. The remora fish are the fish on whales or boats that attach. They have a very efficient attachment mechanism. And so looking at this hitchhiking approach, we can then build robots that attach like this on surfaces, but also underwater. Like this would save energy by having the motion through the environment. You can also do the aerial-aquatic transition with deployable propellers, and this quite effectively move through the environment, even attached to complex like waterfalls and so on. A variation of a similar idea is here, where we have the sail MAF. Now the sail MAF is a sailing flying vehicle which basically looks like that. So it's a flying vehicle that can land, then reconfigure itself, morph into a sailing vehicle, then sail on the water surface for long distances, doing inspection and monitoring tasks. So the sailing itself is, of course, very energy efficient. So it's a very efficient method how to move around lakes or structures without needing a lot of power. So we developed the controller from scratch, all the electronics from scratch, the body, the morphology, did all the CFD optimization, design, and so on, manufacturing, and tested it outdoors. Also showing that it can do the transition from water to air. But of course, there are a lot of challenges on the Reynolds number. So the fluid mechanics on this small scale is very not known. So we needed to really test a lot in water tunnels and so on to get it right, get the balance right, get the forces right, and design right. It has a kind of step system as well on the hull to optimize that and achieve this transition. Eventually, we then went to a lake in Croatia, which is a protected lake, Lake Vrana, where we then tested these robots doing long distance sailing. So over 12 kilometers, it was sailing on the water surface, so on the lake, and collecting environmental acoustic data as well. So very silent sailing, being able to pick up bird species as well, which manual methods would not be able to pick up. So being this kind of silent mingling robot that can integrate with biology, I think also has a lot of potential. So we also wrote a book on that, Sea and Sky, so aerial-aquatic locomotion, which is maybe interesting if you're interested in that area. But I would like to emphasize the approach of how we think about this. So we have the concept, so some kind of new concept, a robot like this doesn't exist. So we then look at that, we build it in the lab, we test it, we optimize it and test it in the field, but then want to use it to collect environmental data, such as the soundscapes, as you see here, which you can then get insights from on how to protect bird species in the environment. So this type of concept to system to insights, I think, is very powerful as an approach. So really integrating the question on the scientific level already in the concept or area in the design, I think is important. Again, this circular coevolution of aspects in the robot. Good, so to close, I would just like to emphasize the next step, right? So we go from biology to superheroes to gods, right? That's a godlike robotics is the kind of ultimate goal. And one of my favorite gods from Greek mythology is Proteus. And Proteus is able to change the shape, right? To move on water, on ground, and so on. This is here from 1531, how Proteus looks like. We asked the generative AI how it could look like today, 24. Not so dissimilar. And basically being the idea that we have a robot that can fly, dive, move on water, sail, and do this by having a soft reconfiguration of the body. So the same locomotory modules and structures for doing that. So this is the goal of the Proteus drone project, where we have these fully soft aerial-aquatic transitions, where we have the same structures doing the motion in air, underwater, through reconfiguration, also the sailing on the water surface. So this is something that we are now very much committed to as a project. So to finish, I would like to emphasize just again the philosophy of how to build such robots. And one of them is something that we call physical AI. Now, physical AI is the ability or is the approach of co-evolving the materials, the design, the controller, and the scientific question alongside as we build and develop the robot. So that's a circular co-development of these disciplines to create lifelike robots. So this is, I think, missing in the academic community quite a lot. It's still very siloed. So there's mechanical engineering, there's computer science, there's chemistry, right? It's like completely separate. But I think this is not helpful. If you want to create lifelike robots, you have to involve and co-create together early on. So this paper talks about skills for physical AI and how we could bring this into university education, for example. The second one is the biological inspiration. So bio-inspired design is a kind of a fluffy term that everyone kind of uses, and people also lose respect for the term, right? Because it's not very defined. It's kind of everything is bio-inspired. So I was unhappy about that. So 2014, I tried to write a paper having a methodological approach of how we can do bio-inspired design. So I call this the bio-inspired robot design paradigm, which has 3 steps. One is that we take inspiration from nature. 2 is that we define the principle, what exactly we want to translate. And 3rd is to implement it in the best possible engineering way, which might look different from biology, but uses the same physical principle that we can understand as well along the way. So I hope this helps in structuring some of these design approaches. I was also quite happy when I saw the keynote of NVIDIA in January, which talks about physical AI as a final goal of AI, right? So I think here is slightly different connotation of just being embodied AI, right? But I think that still it's important that we have to co-evolve the models, the controllers, the body along the way. So I think we cannot start with embodiment, you know, in 20 years. We have to start now and do this from the start. Now, to finish, I would just like to emphasize one more point, and this is the need for not just talent and the community and all of us working together on this, but the need for testing infrastructure. And of course, there are a lot of indoor testing labs at EPFL, Imperial, EMPA. We have different flight arenas and so on. There are outside test beds too, right? I mean, every company might have some test bed for robots. But really what's missing is something that is outdoor or that is outdoor representing, but being instrumented, accessible, and safe like indoor environments. So this is something that we now filled by building the drone hub. The drone hub is exactly that. It's a structure which is embedded into the Nest building in Zurich at EMPA. And the Nest building is a special building. So it's a skeleton, and each unit in that building is a new type of experiment in building technologies. For example, one unit is made of wood materials, so wood in construction, right? What can you do with that? Or one, the top right you see is the hilo, which is very thin roofs, and is a new method of how to manufacture lightweight structures in construction. So it's bridging the gap from laboratory to applications and being tested with people being inside and living inside. Now, the latest unit that we built is called the drone hub. And it looks like that. It's a cage structure that can represent different types of environments for maintenance, for infrastructure, for natural environments. And we started with 3 innovation elements. One is a facade where we can integrate different kind of surfaces to study repair tasks, manufacturing tasks. So it's a kind of lift system where we can install different things. The second one is a biosphere where we have some trees and plants where we can then showcase this biodegradable and biodiversity monitoring robots. And the third will be the integration with the facade, that the robots become themselves like sensing and maintenance agents that are embedded into the facade. A bit like the immune system of the building, where it then senses, self-senses, self-cleans, and self-repairs. So again, the perching being part of the facade as an opportunity to have long duration monitoring, close surface inspection. Also other ways how to integrate with the facade, preventive inspection maintenance. The biodegradation being about new materials and structures being co-evolved with the robots. Can be used for water, also for trees or for agriculture, for biodiversity. And the third being the manufacturing, which is manufacturing of larger structures, but also 3D printing for repair, for example, where we can have different mounting bars to inspect and integrate different systems on it. So the drone hub opened in November last year and is now open actually for industry, for collaboration. So it's a platform, not just for us, it's really for everyone, for the community. So if you have any ideas of something you would like to test there, showcase there, we are very open to have a discussion. We have about 10,000 visitors per year, so it's a quite visible communication platform too. Now, this is part of a new center we are launching called the Competence Center in Sustainability Robotics, where we do exactly that, going from the fundamental research to development to proof of concepts, such as in the drone hub, to really then create a global impact, startups, new technology. So this we have just launched, just received the funding to create that. It's a Swiss-based competence center, but we'll have global collaborators and impact and different case studies. Part of that is the infrastructure, the drone hub being one of them, but also we have a large testing arena, like 35 meters long flight arena in Zurich. And we have at EPFL, for example, the L'Explore platform, which is like a drone hub type of testing asset in Lake Geneva, where also a lot can be tested around underwater inspection, maintenance, and so on. And also we have in Schaffhausen several test beds. And also we tested the robots in Forel. Forel is a sailboat in Greenland at the moment, which can be used for Arctic monitoring and inspection. We just came back last week from testing the robots there. So with this, to summarize, autonomous infrastructure inspection, intelligent inspection, I think can be done with robots, and this includes natural infrastructure, not just man-made. Bio-inspired methods can really help in the robustness and multi-terrain capability, so air, water, air, surface, and also in the transitions. Metamorphosis is an important part in that, having a robot that has different functional modules integrated into the same structure. So not relying on different robots, but having the same robots that can adapt. And physical AI is this co-evolution of disciplines for lifelike robots. It's a philosophical framework of how to do that. Then last point on that is also the drone hub and the testing assets being very important, where we can all collaborate and really showcase how robotics can help all of us, can help the risk reduction, can help in cost reduction, being more efficient, and give a hopeful picture of the future. So with this, I would like to invite you to join us on the journey and do this together. Thank you very much.